Okay, sorry for the lots of delay. Let's begin. Yeah, so maybe you can start with the questions that you have, right? Then we can see where to go. If you have any questions. Sorry, a square. Oh, okay. A is odd. Okay. So this does not require. I think this does not require induction. You can use induction, but so what do you try in this? Mm-hmm. Yes. Yeah. Right. Right. So when you put a equal to, okay, so let's do it formally. So assume that a divides, let's say 2k plus 1 square minus 1, right? So let's assume this. And then what do we need to show? We need to show that it divides for, in place of k, you place k plus 1, right? Yeah. So then this becomes 2k plus 3, right? So how do we do this? Let's, so we can just try to expand this. 2k plus 1 plus 2. So to use the previous case, to use what we have assumed, right? So what is it that we have to show from here? Yeah, so we want to show that, so are we done? Have we proved that? No, right? Yeah, so we do need to simplify. So what is it that we have to do? So this is what we have assumed. And this is what we need to show. So Nagesh, any ideas? So this is something that we have actually, coincidentally, we just did this last time in the number theory class, but we did it in a slightly different way, though it's all similar. But how do we from here show that the last assertion is true? Well, there is a reason why we have written it like this. We want to use the previous case. So using it, what do we have to show? I mean, this is just enough to show that 8 divides. Because that's what we have assumed, right? That's the point of assuming what we have assumed, right? 8 divides this, right? 8 divides this. And so we just need to show that 8 divides this one. How do we do that? Is this clear so far? No, but you have to say, but a is odd, right? So I've assumed it's 2k plus 1. And when you put, so when in place of k, you put k plus 1, you get 2k plus 3. No, that will not work because it's odd. Yeah. But then how do we finish it? How do we show that? Is the last thing obvious? Is the last statement obvious? Yeah, it is divisible by 8, right? There is 4 and there is 1 plus 2k plus 1. This is also even, so there is a factor of 8. Good. So how about we try to show something more interesting, similar but interesting. There is a 2 to the power k. Let's see. So I do not know if induction can be used or not. So obviously, yes, yes. Yeah. Uh, yeah, so that's a catch, right? We need to show that this is true. It's 2 to the k. Okay. So yeah. So the more powers there are here, it turns out that there are more powers of 2 that it is divisible by. It is, I'm not 100% sure about it, but it seems to be correct. Let's try this. We would know, hopefully. So see, it's not a thing that you have to use induction. Okay, you can think really and try to use anything. That's up to you. It is just a similar problem to that one, so I have just tried to let us think about this. Yes, yes, yes. And so do you see this is a similar question to what we did? And so there it was small powers. It was k was equal to 1, but then we had to prove that that is 8. Okay, that's 2 cube. So I think, I mean, this can also be made more stronger. I think harder if you want to say. Put 3 here. That's also true, I think. Sorry, you can put two there. That's also true, I think. But let's just do this one first, then we can think about that. So any ideas? think so. So what can you do when you see an expression like this? 2 to you know, a to the power k minus 1. You mean a to the 2 to the k minus 1, right? Yeah. So you do something like this. Is this what you're saying, Nagesh? Yes, right. So this is the idea we can use. Right? This is a good idea. So now how do we? Sorry. So this is wrong. It's k minus 1. No, that was, yeah. So that's wrong. Yes, right. And this, so see, this 2 is not on the power of k minus 1, obviously, right? It is just the power of that. Yeah? Hey, natural thing. So what will the factorization be? I know it's simple, but please tell me. No, it's a to the power 2 to the power k minus 1. Yeah, minus 1. And so this is just a square minus b square formula. Okay, Satya, if you, okay, so what do we do now? Yes, exactly, right? So you can just continue to do the same thing. Okay, but you can also say that by induction, I mean, to say it rigorously, in fact, to make the thing rigorous, you have to in fact say that by induction, this is divisible by 2 to the k minus 1. Now, obviously, by common sense also, you can continue, right? That's, yeah, that we understand. But in this case, it's enough to do it by common sense. But to be rigorous, you have to say it by induction. Otherwise, it's not clear how why it is true for all k, because you're not showing it. You understand? Anyways, so let me just say, because we are also doing induction topics, so by induction, 2 to the k minus 1 divides a to the k minus 1. Sorry. And so we are done, right? Because 2 to the k minus 1 divides this, and this is even. So I don't need to put so many, this is also even. Yeah. So 2 divides, so this implies that 2 to the k divides the product, which is what we need. Is this nice? Is okay? Yes, yeah, this is the induction hypothesis, which is what should be said when you're writing clearly, is that this is the induction hypothesis. And obviously for small cases, it's trivial to check. Okay. Fine. All right. So this is just a good extension. Yeah, because so how we spotted this was last day we were investigating this for 4 power 2 to the 4, I think, right? 2 to the 4 divides a to the power 4 minus 1, something like that. And there we kind of guessed this result. I mean, we in fact guessed a more general result. I mean, not general, more tighter result. So let me just keep this, right? So what is the more tighter result that we can guess? Because see, it's not coming out of the blue. What I'm trying to say is 2 to the power 3 divides this, sorry, a square minus 1. So when this power is 1, and this power is 1 plus 2, right? So in that, I mean, if you just also try for a to the power 4 or a to the power 2 square, you will see that this becomes, the 3 becomes 4. So the point is that this is a not such a bad guess to make. Okay, so then now we can try to show this. So again, let's think. And this technique that we are using, this kind of factorization, which kind of decreases the power by 1 and not by half, it kind of has that effect. This is, I have seen this being used in many problems, so it's useful, seems to be a useful thing. And we will try to use it in, we will see when we do harder problems or when you do them. So I think it's going to be similar to what we have already done. Yeah, so the question has changed to k, this k has become k plus 3. Yeah, so this is, yeah, so think, so it's good that we have to think a little bit in the class, because thinking on your feet is very important. This is one of the things that I did not do enough when I should have done, and even now I don't do enough. Yeah. So I was presenting my thesis, and in the last I got stuck because I couldn't think on it. The moment the thing got over, I got solved. I solved it. And then I mailed them, so it was got okay. But so this is the thinking on your feet, and obviously this is just a casual, means it's not such a presentation or something. You should think during the class. So I mean, so I think it is the same thing, right? By induction, no. Okay, so let's just assume that we want to do this by induction, the way we have done. So what can you assume? What should you assume about this? Because this gives you 1, 2, right? This gives you 1, I mean, one can use better notation, but this gives you 1, 2, right? So what should we assume? Well, uh-huh. Should we assume this? Yeah, but assuming this is not enough, right? What is it that we have to prove? We have to prove this. Yeah, the k plus 2. This is what we have to prove, right? That 2 to the k plus 2, 2 to the power, yeah, k plus 2 divides this, because that is what the question is. So this is what we should assume. And obviously the base case is what we did at the beginning of the class. That was the base case, right? So even the base case we kind of use induction to prove, but that can be proved. But anyways, the base case was this, right? And so the base case is done. And this is what we will assume. But then again, we are done, right? Because then this gives you, or maybe in that language, I should just give k plus 2. This gives us k plus 2. Yeah. And then you get k plus 3. You see, the question is similar, right? It's just a translation. So you just get that extra 2 in the base case, which is just maintained throughout because the growth is by 1 at each step. Right? And you can now think of many generalizations of this. If in the base case, if you had somehow had this 4, then you could put a 4 here. If for some a, you had a 4, if someone told you, right, that a is 1 mod 4, then you can put a 4 because again, the growth and the base case is the same kind of idea. So induction is good. I mean, here it's not really induction. I mean, in the sense that induction just helps you to formalize something that you already have an intuition of, but fine. Yeah. So is it okay, Satya? You also, is it fine? Let me know. So I see what's going on. Okay. So we are getting into, and these are good results. These are not trivial results. These are okay, good lemmas which you will use. Okay. Throughout. Okay. All right. So let's move on. Right. I mean, so can you think of any more generalizations of this or anything? I don't know, something. Yeah. So there's one question that I can ask, which comes to my mind, and I think that can be a reasonable question. So let's see. I mean, I want to investigate how good is this result that we have proved? And this is not just something that's coming randomly. It means these are actually, some of it is actually a good problem, but that we'll see later when we have more language. But I mean, is this the best possible? Okay, so what I'm asking is find an A, obviously, I mean, find an odd A, find an A such that 2 to the k plus 4, so A is odd, okay, that is there. We just want to say that there is an A for which you cannot do better, okay? So for which 2 to the k plus 4 does not divide, Obviously, there will be an a for which you can do better. That you can always construct. You can just take a to the again be 2 to the power 2 to the power something. You can understand. We just have larger things. But find an a for which there is no larger power, for which 2 to the k plus 4 does not divide a to the 2 to the k minus 1. Should we do this now? Let's do this now. Okay, so this, okay. So let's see, let's think. So Satya, is the question clear? Yes, yes. Okay, good. Good. Okay, so just think. I'll just come. Okay, just think. All right, let's try. So, any ideas? You can think about the simplest possible a, maybe, right? Okay, one is one is one does not work. 3 is the next one. Okay, so that's I mean, you should always think. I mean, it's simple. Yeah. So let's see. Okay. So you're saying this is 3 is the counter, 3 is the answer. Is so let's say that. So take a equal to 3, and then you take k equal to 1, and so then this one becomes, sorry, 1 second. Yeah, why don't we take k equal to, no, wait, 1 second. No, Is this no? Is this no? So have we proved something? So have we proved something incorrect? Yes, right? This was k plus 2, not k plus 3. Is that right? I mean, by induction, you can prove anything if your base case is wrong. So sorry, let's just work out the base case once. Okay. So what was the base case just for the initial question? So we proved that this is divisible by 2 cube. So that was 1 plus 2. That's all we had, right? Okay. So this means that it should just be k plus 2. So that's the first thing. Right. So I mean, by induction, you can take k plus 10 and prove that if you assume base case like that. So that's the problem with induction. Okay, I mean that can go wrong. So this has to be one has to be careful. And let's just run the proof once again. Okay, in case we are making some error, we don't want to keep. Yeah. So then this becomes k minus 1. Yeah, minus 1, and this becomes a to the k minus 1 plus 1, and this gives us 1 2, and by induction, so I think that is what one of you was saying. This is yeah, so this is k plus 1. Right, so by induction hypothesis, this is divisible by 2 to the k plus 1, right? Because that is the base case we have proved. Yeah, two more than this, and so that's k plus 1, and so total we get k plus 2. Yeah, something is still bothering me, but that is probably unnecessary. Yeah, seems correct. Okay. So then it's correct. Can we just check it for some small k just to be more sure? So can we check it for, sorry, so just checking it for a small k, okay? 2 to the 4, and this will, so this will then become 2. So can you explicitly show that this works? And we'll also just, review the factorization technique, right? So let's show it explicitly. This is what we have already shown by induction, but let's just check it more explicitly. I don't know, something is just bothering me, something, but hopefully there's nothing wrong. So a square minus 1, a square plus 1, and then again this is a minus 1, a plus 1, and this is. So can any one of you convince me that this is divisible by 16? Directly, we want to convince that this is divisible by 16. And it's also a very good technique from factors and consecutiveness of factors, and a lot of things can be done. So that's like an independent technique. So we want to show that 16 divides this. Just directly from basic reasoning, A is odd. Let's just try it. So that's easy, right? So like, I mean, A is odd, so this is even, right? This is also even, this is also even. So we get, certainly we get 8, but we want to explain that this is divisible by 16. So how do we say that? Yes, it's divisible by 16, right? Because see, these are two consecutive even numbers, consecutive even numbers. So what does that mean? Well, it means that if one of them is divisible by 2 only and not divisible by 4, then the other one has to be divisible by 4. So one of them has to be divisible by 4, right? That's the extra thing we get. Two consecutive even numbers, one of them has to be divisible by 4. Yes, exactly. Yeah. So that's why I was expecting that. But anyways, so this is divisible by 2. So this is the interesting easy thing. And so it's indeed correct. Okay. So then we'll come back to the original problem. So, but this is a very these ideas of consecutive having somehow this uh, is a very special idea, so a good idea. So what I want to just say, just give a problem on that, and then I'm just coming immediately to that. Okay. But let me just give you this when you guys think about this. So what I wanted to try to show is you take a minus 1, a minus 2, and a minus 3, and show, and just I'm not writing show, but just show that this is divisible by 24. Okay. Any a, now this is any a, so I should maybe write that any a. So you should note this down. All these are very nice problems. And then I want you to further show that this happens. And then you can think or try to find a generalization. So these are part of a bigger picture, and that's why it's so interesting, right? These ideas. Yeah, so note this down and think about it. This will not think now. Take your time and think. Okay. So once you're done noting that down, then we'll come to this question. All right. Okay. So that's, so if there are no doubts here, then we'll come to the question. So we are taking this, yeah. So first of all, this is a, it's fine, k plus 4, but we want to just show for k plus 3. Yeah. So let's just take k, let's just take k equal to 0 first. Yeah, that's what I'll first do. K equal to 0. So then we get this 2 cube. And then what happens? So the a is 3, and k is equal to 0 means this 2 to the power 0. Yeah. And so certainly 2 cubed does not divide this. Yeah. Okay. Yeah, and maybe k equal to 0 should not be taken. Our whole thing is starting from k equal to 1, right? From a square, remember? Because I mean, if it's an odd number, then it could happen that 2 divides it and 4 doesn't divide it, right? So this theorem is not even true for k equal to 0, so we should not be talking about that. Okay. So let's try from k equal to 1. Okay. So then what is it? This becomes 4, and this becomes 3. This 3. This becomes, is this, so is this right? No, this is 2. True. And you can see it's divisible by 8, that we already know that as a general fact for any odd a. It's true. But we want to show that in general. So what is it that we want to show? Let's just write that. Or rather, no, I won't say show, I'll say claim, because we are kind of already in that claim. Claim is that 2 to the k plus 3, the 2 to the k plus 2 divides it, but 2 to the k plus 3 does not divide 3 to the, and this means that the largest power of 2 we have found out. Somehow we have factorization of it up to 4 powers of 2. So how do we do that? Let's think about it. I'm removing this. Please try this. Okay, we'll discuss this next time. So we have checked. So you guys just think. I'm just writing things, just collecting the things here. And maybe we can also write so we can again induction. I don't know if it will work, but does not divide. Same thing, right? So the same thing works. So Nagesh, then tell us the more details. Hmm. You mean 3 to the power, right? Exactly. Yeah. So we break it. So as you said, it's the same thing. So we break it like this. And then yeah, okay, 2 divides this. So okay, so 2 divides this. Yes, so from the assumption, we know that this contributes exactly 2 to the power k plus 1, right? The contribution is exactly k plus 1 from the first factor. Is that right with everyone? Right? By induction, we know that the contribution of this is exactly 2 to the k plus 1. K plus 2 doesn't divide. 2 to the k plus 2 doesn't divide. But then if you want to show that, I mean, the overall contribution, overall power is k plus 2 and not more, then you would want to show that this is divisible by 2, but not divisible by 4. Is this point okay? Right? So we want to show that 2 to the k plus 3 does not divide this. Okay, and we know that by induction that 2 to the k plus 2 doesn't divide this first factor. But then we have to show that the second factor is not divisible by 2 square. I mean, otherwise the sum will become k plus 3, right? K plus 1 plus 2. Okay, so we want to then show, basically the growth is controlled, right? You can think of it in any way. Show that we want to show that 4 does not divide. So you must realize that we need to show this. That is the main thing. Yeah, the largest power is k plus 2 we want to show. And here we have k plus 1 already. So here the largest power should be 1. Largest power of 2 should be 1. And that's, we want to show that 2 square doesn't divide. So how do we show that 4 does not divide that thing? That's another thing we have to show. But it's a 1, right? That's a plus 1. Is that? That's a plus 1. Uh, yeah, but if you give the k of value to be 1, then what happens? Oh, yeah, then 1 minus 1 becomes 0. Oh, so then it is indeed correct. So then what happens? Oh, so that's right. That's right. So then is it not correct? Is the statement not correct? So for k plus 1, for k equal to 1, that is the case. But what if I say k, let's say k bigger than 2? Because see, for us the k is not 1. K1 we have kind of already done, right? So what I'm just trying to say is you're right, and it doesn't work for k equal to 1. But for k equal to 1, we have already checked that this is true, right? So now we can move to assume that k is at least 2. That's a good point. But now we can assume that k is at least 2. Okay. But when k is at least 2, then you see, then what happens? Then this thing is like, whatever this inside thing is, it's like a perfect square, right? And it's a perfect square plus 1. Okay. And k is at least 2. So, I mean, this will be k minus 2. So here k is at least 2. Then it's a perfect square plus 1. So it is just some x square plus 1. I can write it because k is at least 2. Now this is easy to show is not divisible by 4. Right? Well, because I mean, if x, I mean, so you can just do some model arithmetic if you want to do that. Otherwise, it's not, you don't have to do it. If you assume that, I mean, if you assume that x is like 4m plus 3, right? But when you square it and you work out the things, it becomes some 4s plus 1. It's 1 modulo 4. It's what I'm just trying to say, right? After squaring. And then when you add a 1, it becomes 4s plus 2. Not divisible by 4. Okay. And when obviously it's, if it is 4m plus 1 case, then it's even straightforward. Okay. The point that I'm trying to make is that x square is always 1 mod 4, which is actually something that I've already shown. It's even 1 mod 8. So then when you add 1, you get 2 mod. But yes, for this, we need k to be at least 2. But then that's fine. The k equal to 1 case we have already shown. And so the k is at least 2. Okay. K is at least 2. And then this seems to be correct. Okay. So then are we done? Or is there something that we are missing? So, I mean, I think it is fine, right? Yeah, so this seems correct because see, our base case was k equal to 1 here. And then using that, you can, but just a minute. So when you go to, no, but there is a slight problem still, which I am seeing. So our base case was on k equal to 1. Okay. So, but then when you go to k equal to at least 2, Yeah, so it's fine, because when you go to k equal to at least 2, when you go to k equal to 2, then you here it comes to k minus 1, this becomes 1, and so you can use the induction hypothesis. And here also k is at least 2, so k minus 1 is at least 1, so it is a square, and so you can say it's not divisible by 4, and you can then, so it's right. Makes sense, right? It's a subtle thing, but also there is a, you can feel that there is something interesting going on, right? There is something nice going on here. And so let's just keep the claim that we have. So you see, this was a nice just application of induction, a little bit of number theory here and there, but we have proved this. When you have better notations, it will be better, but far we have proved this. Okay. See, this highest, maybe I can just mention this, is that this highest power that a prime, or rather 2 here, is dividing an expression like this, okay, or any expression, in fact. I mean, this has a notation, and that notation is maybe something good to get used to. Maybe I can just mention it now. Is you can also just say it like this, that the valuation of this, yeah, you can also just say that the valuation of this at 2, this is just the valuation, we say valuation of this with respect to 2 is k plus 3. Okay, this is just a notation that we use. Okay, and this is to denote the highest power. In more elementary ways, it is another notation which is turns out the same as I was going to, is this. This is also written like this. Okay? The highest power that something divides something is also written like this. So that this divides this, but no higher power divides it. Okay. So anyway, this is just rough notation. So what we have learned is this, and we have learned that for some it divides. Okay, but then you can kind of notice that in general, it seems like the highest power that an expression like this, maybe now we can further generalize it, an expression like this, right? The highest power of 2 that is dividing this, the highest power of 2 that is dividing this kind of expression in general, obviously a has to be odd to begin with, otherwise there is no power, so k is 0, so it's not interesting. Depends on the, so this we can already feel depends on what power of 2, just question mark maybe, what power of 2 divides n. Yeah, and it also, and I don't know if you guys have sensed that, also depends on what power of 2 divides a minus 1. Lastly, also we saw a little bit of that, right? It depends, when you do keep doing the induction, finally it comes down to that, if that is what you can feel, right? Depends on these, and in fact these things are very precisely related. That is the good thing. So this depends on has a very precise relation. So far, what have we seen? Yeah, so far what we seem to have seen is that this k, yeah. So maybe if this highest power is t and s, right? Then this k seems to be at least t plus s. Yeah, you guys agree? Because that when that thing was k, so when n has k powers of 2, or when what we did was a special case kind of, when k was, when this n was exactly that 2 to the k, but in general you can prove it, that when n has k powers of 2, yeah, sorry, when n has t powers of 2, right, And if a minus 1, is even, so it has, let's say, s powers. In our case, it was 1 power, right? Then what we are divisible by is t plus 1. In fact, it was t plus 2, right? So this is, in general, this is what will be, seems to be correct. That if there are more powers which divide a minus 1, you can kind of build on that induction case, sort of, you can feel that, is that it is this. And but then there is a, with some more plus minus 1, there is a more precise relation that can be given. That's number one. And number two, you can generalize this to other primes and other prime powers. You can generalize this to primes, other primes, but then the is slightly different, but the methods are similar. Okay? So these are the things that we can explore in the future, maybe after 4 or 5 classes, but you can think about these things and try to see if you, yeah, this material of this is available to read, but it's little technical to read. Okay, so maybe, yeah, you can see if you can read it, it's very good, then you can tell me. Okay, yeah, but we have explored all this naturally, and that's important. So then that's it, they'll end the class, but then I'll just give you 2 more problems which are simple and approachable, so you can try on the same ideas that we have ended up discussing today. That was not the plan, but I mean, that's the thing. I mean, we are learning things relevant and moving forward in a natural way. Okay. So the question that I would like to ask naturally is, which is naturally connected with the things we've done, is find, and you can try to do it special case also. Always, if you cannot do something, don't leave it. Try it for special cases and so on. Find the GCD